Okay, in the interest of this video not being crazy long, I'm just going to do the induction at the end, recognizing that if we had done this all the way through, we would have solved all of these problems, and some of these things are going to have helped us. So, prove by mathematical induction that the arg of Wn is the same as the arctan of n plus 1. Well, in order for that to work, we have to define what Wn is. And Wn is the product is that right there. So if I start from n equals 0, which is my base case, I would end up with the argument of 0 squared plus 0 plus 1 plus I. And if I did that, that would be the argument of 1 plus I. And that just turns into the arctan of 1 over 1, which is 1. And my other one would be the arctan of 0 plus 1, which is the arctan of 1. Those are equal to each other. We can stop there. We've done that. The next thing we have to do is we have to get our, when n equals k, we're going to assume that this is true. So if we assume that that's true, that means that if I was to do the argument of the product from n equals 0 all the way to k of k squared plus k plus 1 plus I would get the arctan of n plus 1. Sorry, the arctan of k plus 1. And I can write k plus 1. All right, so we have that assumption. We're going to move on to our induction step, which is we got to prove it true for n equals k plus 1. Okay, so that would be the argument of from n equals 0 all the way to k of k squared plus k plus 1 plus I. All of that, and then we just multiply it by the next step, which would be k plus 1 squared plus k plus 1 plus I. And that would end up being my value. The reason why I did it that way is this right here is this. Okay? So if I substitute in the argument of the arctan of k plus 1 times this thing here, which is k plus 1 squared plus k plus I, right, I would end up with something like that. Actually, I didn't want to do that step just yet. I wanted to leave it because I've got a principle here that I can use. And the principle I can use is when you take the argument of x times y, it is the same as the arg of x plus the arg of y. That's just one of those rules of the arguments of complex numbers. So, rewriting this now, well, this is that part. So I can just rewrite that as the arctan of k plus 1 plus, well, the arg of y is going to be the arctan of 1 over, and I'm going to go ahead and expand this before I go any further. So that would be k squared plus 2k plus 1 plus k. I forgot when I did this to add my extra plus 1, plus k plus 1 plus 1, which will give me k squared plus 3k plus 3 plus I, right? So my i's already accounted for in the top there, but this turns into k squared plus 3k plus 3, and that gets me somewhere, and it's mostly because of this. We know that if I add the arctan of A plus the arctan of B, I get that combo. So that combo is going to give me, and this is so much fun, this is going to be the same as the arctan of k plus 1 plus 1 over k squared plus 3k plus 3 all over 1 minus the product of k plus 1 times 1 over k squared plus 3k plus 3. Whew. All right, before I go any further on this, I'm going to turn this denominator into a rational function. So to turn that into a rational function, I'm just going to multiply this 1 by k squared plus 3k plus 3 over k squared plus 3k plus 3. And that will result in this being k squared plus 3k plus 3 minus k minus 1 from here all over k squared plus 3k plus 3. There is an advantage to this. I'm going to simplify it though. So k squared plus 2k plus 2 over k squared plus 3k plus 3. So that's my new denominator. So let's get that written out so I have it. So I've got the arctan of k plus 1 plus 1 over k squared plus 3k plus 3 all over, because I'm lazy. Now, when I divide by a fraction, I take the reciprocal and multiply. So if I was to do that, my denominator is going to turn into k squared plus 2k plus 2, but now I have to multiply this through the top. Notice this here is going to go to 1. And then when I multiply that here, I'll end up with k plus 1, k squared plus 3k plus 3, and then plus 1. Again, we're still taking the arctan. All right. Let us expand that bracket and see what we have. So I'd have the arctan of, that's going to be k cubed plus 3k squared plus 3k, and then plus k squared plus 3k plus 3. All of that turns into k cubed plus 4k squared plus 6k plus 3, but then I also have to add 1, so plus 4. Okay, writing that out. K cubed plus 4k squared plus 6k plus 4 all over k squared plus 2k plus 2. Now, here I'm going to use a little bit of fuzzy math. And the reason why I'm going to be able to get away with this is that we know that at the end of the day, this has got to equal the arc tan of k plus 1 plus 1, or k plus 2. So I am going to guess that if I do this polynomial division, I'm going to get a k plus 2 out of it. Let's quickly try this. So k cubed plus 4k squared plus 6k plus 4. If I divide into that, k squared plus 2k plus 2, well, for that first bit, I'd have to multiply by k, and I would have minus k cubed plus 2k squared plus 2k. When I subtract, that turns into 2k squared plus 4k plus 4. And then I would have to multiply by 2 again, and I'd get minus 2k squared plus 4k plus 4. That's going to 0. So we know that that is a factor. And we also know then that this is k plus 2 times k squared plus 2k plus 2 all over k squared plus 2k plus 2. Those cancel. I'm left with arc tan of k plus 2, which is exactly what we were trying to get. Sweet God, that took forever. Then we would have to make the statement that because it is true for n equals 0 and can be proven true for n equals k plus 1 when n equals k is assumed to be true, it is proven for all natural numbers. The reason why I did natural numbers is right there. We're told that we're dealing with natural numbers. Holy cats, we did it. Hope that's helpful.